Kai, and I'm mainly talking about today the building the scalable and the flexible Baremetal Kubernetes cluster in the layer 3 fabric with Talos. So maybe start with some introduction of myself. So my name is Zhang Kai, and I started the journey with NesK in Nokia since 2019 as a cloud platform architect. Now I'm leading the Nokia Kubernetes Service NKS workstream. In the past, I have been doing the cloud architect for the OpenStack and VMware platforms, and also technical support and the system engineer for Nokia value-added service. In my early time, I have been doing the network engineer for operators. So that's about me, and let's go to the topic. So this is the overview of the NesK, Nokia Enterprise and Service Cloud, which is one of the world's largest private cloud. My colleagues Yanni and Timo already went through the introduction of the NesK, so I will not go through deeply here. But several key points is that we have quite many cores running in many data centers across the world. And part of them, we have more than 120,000 cores running on Kubernetes. And some are as virtual machines, some are as Metal. And the Metal is the one I'm focusing on today in this session. One key is we're running all the solution with 100% open source component. We build them up with, of course, some of our own glues to make them work together. We have like more than 11,000 servers, physical servers, I mean, in those data centers. So automation is the key. So we need to automate many works. Otherwise, we cannot manually manage that many servers. Moving forward, this is the main topic. Okay, Kubernetes servers Metal. So basically, we started with NKS Virtual, which is the virtual machine based on solution, and around maybe 2 years or 2 years ago, we started to get the requirement from the customers. They may want to run the Kubernetes on bare metal for better performance, for example, and we start to build the new offering, and we're aiming for several principles for the choices of the technologies. Mainly, they are driven by security, operational efficiency, flexibility, and also the needs to embrace native cloud Kubernetes technology trend. So the NKS Metal is aimed for large clusters, like, for example, more than 1,000 CPU cores. If they are too small, it doesn't make sense to run on bare metal, since we have to spend several servers for control plane that already eat up several hundreds of cores. So it makes sense only if it goes large enough. And the architecture is more like pluggable or modulable, and which enable us to change the component fast, because this is also the fact that there are fast-moving technologies in the open source communities. So that enables us to switch the component fast. The OS choice, though, we try to make it minimal, and that is also a big reason for us to choose the Talos. Keep it minimal, secure, and it's built to run the Kubernetes. That is the purpose made. For the deployment, we're targeting to have the cluster API to go with the Kubernetes native way to manage Kubernetes clusters lifecycle, to use Kubernetes to deploy Kubernetes, kind of. And the network is also the key focusing topic today. to build the flexibility, to have the flexibility of the clusters, we are targeting to run the routing on the host with BGP, and the network. We build a new fabric with the layer 3 only. Then there's no layer 2 domain anywhere, even between the servers, between the server and the switch. They are all point-to-point layer 3 connections. And I will explain more for the network part in the following slides. And storage, we have already went through in last session. We have the external dedicated safe storage, which serving multiple purpose for OpenStack, and here for the Kubernetes, the safe storage is configured as a storage class with a safe CSI. The user can create a PVC out of it. And aside, we have also some monitoring component for user to use that is managed by the NK's API. Timo went through that. A bit reasoning why Talos, and it's immutable and the minimal footprint, which matches to our requirement. And it's a secure, it's a read-only root file system. It has relatively small attack surface. You can access it only through the API. There's no SSH to it. And it provides the full set of the cluster API providers, like the Bootstrap provider, control plane provider, the Cedero infra providers. So that helps us to automate the cluster lifecycle management for deploying and upgrade and destroying the clusters. So everything is API driven, so that is better for our automation. We can easily manage the managed clusters as code. All the OS configurations are also as code. They're all configured through, like on the right side, the example of the machine config. So everything is like declarable there in the machine configs. So we can easily manipulate this configuration for every server in as code. That helps a lot in the automation. If I go further, so this is the data center foundation for the Baremetal Kubernetes clusters. We have got several key design targets. So we used to have a kind of a traditional fabric, which is the access aggregation core, those type of tiers, 3 tiers network architecture. And we were building the new our architecture for the new fabric for the NK's Metal. We decided to go the leaf spine, more modern one, and we decided to adopt a layer 3 only approach, even between the server and leaves. So there will be no layer 2 between any 2 endpoints. That requires us to run the BGP routing on the host. So every single server is independent. So every single server is like plugged into the fabric through the leaf switches, joining the BGP routing, and advertise its own node IPs or whatever IPs it advertised there. So that gives us some good benefit, like we can put all the servers into a common pool, no matter which rack the server is installed, it doesn't matter. It anyway independently participating in the network fabric. Then with the server pool, we can easily create the clusters across the racks. We can pick up any server from any rack to form a cluster. So that we can totally forget the concept of the rack. So we only talk about the servers. And with this flexibility, we can easily also remove the server from the cluster, give it back to the pool, or on the other hand, we can easily scale out. We can easily add a new rack into the server pool, and those new servers can be easily added to the existing clusters. There's no limitation from network point of view. We don't need to care about the racks. About installation or deployment or bootstrap, how this is done in this new architecture. As I said, we have a new fabric with the servers, and we have the netbox inventory to document all the racks, all these data center resources, including racks, servers, switches, IP configurations, everything in the data center. But to facilitate the cluster level operation, cluster level resource allocation, we build up this resource API, REST API, which we expose to the deployer. The deployer is the NKS API where Timo went through in the last session. So when we need to create a new cluster, when we have a request, need to create a new cluster, deployer will ask for the resource API, like I need a new cluster with 20 servers, and the resource API go to the inventory and check the free server pool and allocate. If there are enough free servers, it allocates 20 servers for the new cluster request, and then we get this list of allocated servers hanging around. And the default policy, default logic is to allocate as servers from as many racks as possible to get better availability and to get better rack level usage or balanced allocation. So at the moment, the server just got allocated, but they are not connected. So by default, all the servers, if they are staying in the pool as free servers, so they are disconnected and powered off from the network and power point of view. And we need another part to configure the network for them. Then we create another API called the SDN API, which does that part. So when resource API created a cluster, allocated the server, it asks the SDN API to configure the switch port for those servers and allocate IP from the IPAM, which is also netbox here, and also notify the DHCP to prepare the PXE boot environment. PXE boot will be used to bootstrap those servers in the later installation phase. And once it's finished, it returns to the API. Sorry. And in the end, the data center resource API return back to the deployer with list of allocated server and the information of the server, including the IP addresses, for example. So with those information, the deployer can render the cluster API template for the target cluster to be created. And those templates will be deployed to the management plan. Management plan is actually a management Kubernetes cluster. It runs the cluster API with Talos Bootstrap provider, control plane provider, infra provider, and the CDRO manager. That helps to further bootstrap the node through the PXE, since the CDRO manager has PXE, has a TFTP server to assist the PXE boot. And it has metadata server to deliver the machine config for each server. So it bootstrap the server through the IPME power control and install the Talos and bootstrap the control plan and register the worker nodes to the control plane. Then we have a running cluster. So that is the whole procedure, how we bootstrap the node, the cluster. If we're going forward, this in the beginning, this was challenging for us. Like as I said, every node it's like joining the fabric at the layer 3 point. We need to achieve the routing on the host, and we tested and used the FRR to be the BGP speaker on the host. And we started to run it as a static port. Then later, once Talos support the system extension, we move it to run as the Talos system extension. So it starts kind of as a native service together with other Talos service. When nodes start up, it start up together, then provides the network for the host. There are 4 links between the node and the 2 leaf switches, and BGP unnumbered peering is happening between the FRR and the leaves. So with BGP unnumbered peering, we don't have to configure IPv4 address. We're using IPv6 link local address for the BGP peering. So that saves IP address space. That saves also the complexity of allocating and recycling those IPs. Then we have the BGP peers between the FRR and the leaf switches. The node IP is actually configured on a dummy 0 interface with the /32 address. The node IP is configured to the kubelet to represent the node, and it is advertised through the BGP to the fabric. So on the control plane node, we have also this on dummy 1, we have the Kubernetes API VIP, which is also advertised through the BGP to the fabric. So on the same node, we have also the MetalLB BGP speaker runs on every node as a daemon set. It pairs locally with the FRR through a virtual Ethernet pair. That is used for MetalLB to advertise the Kubernetes load balancer service IPs. So every cluster gets a subnet of the IPs. So MetalLB can use them, can allocate IP from them and allocate them to the service, to the load balancer service. They get further advertised through the FRR, then the routes get further imported by the FRR, then advertised further to the fabric. Then from the fabric, we can reach those services. So the manifest of the FRR Talos extension is available on the GitHub. So if you are interested, you can go there and take a look. And you can also build your own for your environment with some modification. And also there's the /31, which is the PXE boot interface only on the first interface. And this bootstrap is only needed on the boot up time, and it is not in use during running time, since during running time, we're using the BGP route. Yeah, BGP peers on the host. So this is the kind of output of the FRR CLI. So on the upper side, it's the default VRF. We can see through 4 interfaces, we have 4 peers, 4 neighbors. But they are like from the 2 leaf switches. Another side is from the VRF MetalLB. This is the local MetalLB BGP speaker. So in total, we have 5 neighbors from the FRR point of view, and we can see the state like prefix received. It's a 7, which means the MetalLB is advertising 7 service load balancer service IPs, which we can see from this slide. This is the output of the Talos GET address, what interface and what IP we have. So first two are dummy 0 and 1. They are representing node IP and Kubernetes VIP /32 IPs. On the ETH 0, we can see the /31 is for the PXE boot. This IP, we get it from the DHCP. Then we have IPv6 link local address on each of the interface. They are used for BGP peering with the leaf. Then we have the VETHB, which is used as a point-to-point connection to the MetalLB speaker locally. Another end is running in the MetalLB namespace, so it doesn't show here. The lower part is the show IP route output. So the first 4 lines, it represents the BGP default routes towards the fabric. We can see they all have the same weight. They're running in kind of equal-cost multipath ECMP mode with load balancing. So we have 4. We have 4 active uplinks, which makes up like 100 gigabit per second bandwidth in total for the single node. And the green box we have like we saw last slide. There are seven prefixes. Those are all advertised from the MetalLB VRF. So they are the 7 service load balancer service IPs, which is supporting the service with port running on this node. The last 2 are the connected routes, represent the node IP and the Kubernetes API VIP. Yeah, I think this is the last slide I have. MetalLB, we're using MetalLB for the BGP-based load balancer service. So this is also like a challenging part when we start to deploy this one. We kind of need to use the BGP to do this load balancer service. There are several options. Technically, we can pair the BGP, we can pair the MetalLB BGP speaker with the leaf switch or spine switches even, but that makes the automation and configuration much more difficult. In the end, we found the way we can directly pair locally with FRR, and then the configuration, the P2P/31 IP range and the AS number on both sides can be hard-coded to the same and on every node, because they are not advertised to the fabric. It's only internal, only locally on every node. So that keeps the whole solution much more simple. Here we have 2 pictures. So on the left, it's the default external traffic policy for the load balancer service. So by default, a load balancer IP is kind of advertised from every node when we have the MetalLB speaker running. That is the default behavior, but it's not optimal actually. It may go, if one cluster has 100 nodes, then every node, so we have 100 nodes, they are all advertising the same IP, even there's no port backing that service, backing that deployment or service running there. So which means from the fabric, the traffic can reach any of those nodes, then go a detour, then get netted to the final nodes, then to the port. And the optimal way in this setup is on the right to use the local external traffic policy. In this model, only the node with running ports for that service will get those IP, will get those load balancer service IP advertised. And once it gets the traffic, it will forward the traffic only to the local port. It doesn't go to another node. So this is the shortest path from the source to the destination. And one also benefit is the source IP is preserved in this mode. I think that's all I want to show. I'm not sure if there's any questions. Can I see?
That was awesome. Thanks, Kai. I have a question. So all your servers are multi-homed, right? How, if you lose a top-of-rack switch, how quickly does it reconverge?
If we lose one,
yeah.
If we lose one, there's no. I think there's no any break at all.
No, there must be some BGP convergence time.
We have also this BFD running between every node in the FRR, between the FRR and the leaf switch, which makes sure it cover reconverge fast enough.
So it's triggering off link state, not just off BGP keep libs.
Not only, yeah.
Yeah, nice. How do you prevent binding MetalLB and FRR both to port 179?
Sorry, where is the question?
Over on the left at the bottom.
How do you achieve this local external object? Is it by peering? Local external object. I'm not sure I understand what
I
is
think
local.
he means the right-hand side of the last slide, where you peer it through the shortest path.
How do you achieve this local external? You mean the last slides? This one?
Yeah, on the right-hand side.
I still don't. I'm not sure if I understand the question, but anyway, the MetalLB is pairing with FRR locally. So it advertised the IP to the FRR. FRR further import the routes from the MetalLB VRF and further advertise it to the fabric, as I explained in the last slides. I'm not sure if that answered the question. Okay, thanks.
Yeah, Nico had a question above that about binding MetalLB and FRR both to port 179. Is that an issue?
Good question. They are running on different IPs in different namespaces. So there's no conflict. That is the way we avoid the conflicts. So MetalLB is actually running in MetalLB namespace with the /31 IP pairs to connect to the default to the FRR, which is running in the default namespace. They are connected through the local virtual Ethernet pair created under the Linux.
Gotcha. That makes sense. Any other questions coming in at the moment? No? What brand of networking hardware are you running? I think.
Yeah, good point. Yeah, it's a. What is the brand of it? It's a Dell or something.
Dell.
But
Yanni said that switches are Dell and running Sonic.
Yeah, the more important thing is running open source network operating system Sonic. So we can easily switch to any white box switches without changing our automation. Our STing API is the one to program those switches through the Sonic APIs.
Cool. Awesome. Well, that was a great talk, and again, on time. So now we have a break until 1:15, unless there's any further questions. Yanni always wants us to expect a typo in that one, and we've got a typo in that one because always only has one L. What are you using for hardware provisioning?
Hardware provisioning, we're using cluster API with Sidero providers.
How big is your smallest compute node? Because you said these are only for large-scale clusters with thousands of cores. So what's the smallest node size you run? How many cores in a node, in a worker?
How many cores per node?
Yeah.
Well, our flavor has per node. It's like it can have like 64 cores. Recently, we have 128 cores per server.
Yeah. Awesome. So big scale.
Yeah, for the size of the cluster, we have, of course, the minimum cluster is 3+3, for example, but we don't really recommend to go that. It's kind of a waste of the resources on the control plane. We do have a larger cluster with more than 100 worker nodes with 3 master nodes.
Have you ever seen a need to go beyond 3 control plane nodes?
For biggest one, it works okay, quite okay. The control plane are having quite low load. I don't see there's a need to scale up to 5 at the moment.
Okay.
At scale.
Are you running KubeVirt on your virtual machines? You are, aren't you? Yeah.
It's up to the end user.
Right. You provision the cluster, and they
we don't really care. User has admin right of the cluster, and we do know some users are using KubeVirt to run some virtual machine for some traditional OS.
Right.
Any plan to move beyond the MetalLB? Move beyond.
What's beyond?
Yeah, I don't know what does that mean. With Cilium or such. We're using Cilium as CNI, but it's pure CNI. There's no BGP or what other fancy functions. I know Cilium has recently somehow integrated MetalLB kind of function into it, but I don't find it fits to our scenarios. One of the trouble we had also during building this up, it's the CNI choices. Not every CNI works with our network setup, with routing and host, with BGP, which is a bit special. Not so many people are doing that. So in the end, the Cilium kind of works, but it's a bit buggy. And for example, we cannot use eBPF-based masquerading. We have to fall back to the IP table-based ways. Since it's not like working, there's bugs need to be fixed. And moving over time, I think it's improving. And I think from next release, we will move to the eBPF-based masquerading for SNAP traffic.
Awesome. All right. Thanks very much, Kai.
Yeah.
All right. Now there's about a 5-minute break until the next talk, which is about PowerFlex and using Omni, our newest product that deploys Talos at the edge to build the future of renewable energy. So we'll see you all in that session. Thanks.
Thank you. See you.